them to share data and get insights out of this data. So on the more technical side of things, of course, sort of the structure of these applications can vary a lot. So this is just one example, so you can kind of see how different devices sort of work together to extract insights from the data they might collect. So this is something called federated learning, which some of you may have heard of before. It's been a very hot topic in academia for the past several years. And the idea behind federated learning is you have a bunch of what we call client devices. So for example, this could be drones, this could be laptop servers, whatever. They're collecting some data, right? Maybe they're collecting some images. And the idea is they would like to collectively learn a model over all of this data. And the way that they do that is they each have a copy of the model. They compute some sort of update to the model based on the data that they're collecting. And then every so often, they send their updated model to what we call a parameter server. And the job of the parameter server is just to collect the updates from all these different clients and average all of them. So now we have one global model that gets sent back to all the clients. And then each client has, again, the job of taking this new global model and using its local data to update the model. So if you are familiar with machine learning, these updates are typically just stochastic gradient descent updates. So nothing too fancy. But I included this here again, so you can see kind of the structure of how we have distributed devices that are all computing something, and those computations are all sort of being collectively used to learn a model. And then that model, of course, can now be deployed on these client devices on new data to extract insights from that data. And there's many, many variants of federated learning. So sometimes you don't have a server. Then, of course, the communication pattern among devices changes. And now we need our communication networks to support that. Typically, that means devices have to communicate with each other directly. There can be a lot of heterogeneity here. So for example, if you imagine these clients are sort of drones flying around, some of them are running low on batteries, so maybe they can't collect as much data, maybe they can't communicate as often with the server. And now your application has to account for these sorts of resource constraints at some of these clients. And the other big challenge that we see in federated learning, and more generally in IoT networks, is that these are often very dynamic systems. So again, going back to the example of drones sort of collecting videos of different areas, these drones are flying around, right? So they're always collecting images of different environments. Their connectivity to this aggregation server or to a base station may be changing. And we have to handle that. We have to make sure that our communication infrastructure is robust enough so that even as this communication quality changes, we are still able to learn something useful out of this application. And this is not just, this doesn't just happen in federated learning. In fact, resource constraints and dynamics are inherent challenges in IoT networks, simply because these IoT devices are often very small, often very resource constrained, and very often do not have reliable access to power. So if we look more broadly at the challenge of we need to sort of figure out how to distribute the work across all these different devices. So the way that we're going to do that, or the way that we're going to formulate this problem in this talk, this is starting to get into the technical part of things, is we model an application as a directed acyclic graph of tasks, and these tasks may be placed on a subset of devices within the network. So this is an example of a graph from one of our autonomous vehicle collaborators. So you can see there's all these different tasks that have to do with processing information at cameras, from LiDARs, from CAVs. And then all these different tasks, the results of these tasks have to be communicated to other tasks. So for example, here you see there's 4 different cameras. We have to analyze their outputs, and then we have to fuse that somehow, again, to extract insights from what these cameras are collectively seeing. And then what we would like to do is we would like to make sure that sort of all these tasks have enough resources to run as needed, even though these CAVs are kind of moving all around the city, so we may have to kind of reallocate resources to make sure that they can, talk to whoever they need to talk to in order to get this application working. And this is kind of a simpler example of an adjustment you might have to make. So again, if you consider a vehicle, it's trying to process, let's say it's LiDAR cameras, it has to talk to, let's say, a roadside unit in order to make sense of the data that it's collecting. Now, as it moves around, it may lose connectivity with a particular server or base station, and now we have to migrate whoever it was talking to here to the new server or base station that's closest to where this car presently is. So we have a lot of dynamics that have to sort of happen here. And you can probably imagine, and I mean, you can see here, this is not a super complicated application, but there's still a ton of tasks that have to be sort of managed, that have to communicate with each other. And you can imagine for some of these more complicated applications, these graphs can be really, really large. So there can be a lot of stuff to coordinate. There's a lot of communication happening at different time scales with all these dynamics of these devices dropping in and out of connectivity potentially. So there's just a lot of stuff to coordinate, and that becomes a very, very difficult problem to do, especially because all of this has to be done in real time. You can't wait like 5 minutes to say, oh, okay, now I realize that the car moved. So now I have to sort of move my application to work on this base station instead of that base station. You really have to do this, again, in near real time. So these are the challenges that we're going to try to solve. And I've divided this talk into 2 different parts. So the first part is distributing computing tasks in dynamic environments, trying to figure out who gets to run which tasks when. And ensuring resilience to changes in the available resources. Again, in the IoT setting, we have a lot of dynamics in the availability of IoT devices. And basically, the solution here is going to be, we designed a really cool reinforcement learning-based algorithm that tells us what has to run where at what time and adapts as the environment changes. Now, the second part of the talk is going to focus more on the communication part of things. And here our goal is learning how do we allocate communication resources to these heterogeneous users. So one of the things you might have realized about this sort of model of an application, although I wasn't explicit about it, is that these tasks are all different, right? They may be processing, for example, different types of data. They may be learning slightly different models. And that means that the amount of data they need to communicate to each other is also going to be different. And again, they may do this on different timescales. The communication may have different priorities if we're talking about multiple applications trying to run over a communication network. So here, for example, if you have a bunch of sensors trying to collect data, maybe some of that data is really, really crucial because, I don't know, it's in the path of a natural disaster or something, and you have to monitor how that disaster is moving through the space. Maybe other data is not super crucial because you already kind of know what's going on in that particular area. So you'll have a lot of very heterogeneous data that has to be communicated. And our question is, well, how do we figure out sort of how to allocate resources so that the important tasks get the resources they need, perhaps at the expense of these less important tasks. So how do we learn how to do that, and how do we learn to do that quickly so that we can actually sort of execute these decisions without waiting until they don't matter anymore. All right, so these are the 2 questions that I'll be addressing in this talk. So the first work on distributing computing tasks across heterogeneous networks. This appeared last year in MLSys 2023. And I've also put the link here to our archive paper in case you're interested in more details. All right, so I already introduced this a little bit, but we have a distributed application here, which we model as a directed acyclic graph of what we call tasks. So each task is basically just some computations that have to be done. And again, these tasks talk to each other. So maybe here you do some pre-processing on a stream of data, and then you send the pre-processed results. Maybe here this is a neural network, so you have to now pass your pre-processed results through a neural network, and then that gets sent to another task. Maybe it gets combined with the results of another neural network, and then you get some kind of output of this application. So this is a very, very general model of an IoT application. And now our problem is to say, well, each of these tasks has to do some sort of computing, has to talk to some other tasks, and each of them can run on a subset of IoT devices within our network. So this is a highly abstracted view. So here we have a bunch of candidate machines. You can see they have different heights, they have different busyness, so they're all different. And we have to figure out what gets to run where. So again, you can imagine in an IoT setting, maybe you have sensors that collect the data. So the data collection task has to be at those sensors. But then where you process the data, that could happen anywhere in the network. It could happen at the sensors. It could happen at an edge server. It could happen at a base station. And we really want to optimize where this happens in order to be sort of efficient and timely in how we process the data. All right. So we capture these more formally in our problem formulation by saying that data transfer between tasks is modeled as edges in our directed acyclic graph. And we say each device has finite capacity. Each edge between the devices is a communication capabilities. So this also has finite capacity. And naturally, each task requires some sort of computing and communication resources. So we have some constraints about which tasks or which devices have enough resources to run which task and which devices have enough communication resources to actually communicate to another task on another device. And our goal here is going to be how do we place these tasks on these devices to minimize the overall finishing time of the application? All right. So if you study computer science, you might have realized that this is actually a very classical problem in computer science. This idea of you have a graph here, you have a graph here, and you're trying to match the nodes in the graph subject to various constraints on these placements. Again, this is a very classical problem. What makes it different in our setting is that it's also a very dynamic problem. So the structure of this graph might change, the resource constraints might change over time. So we need a solution that's going to really adapt very quickly over time. All right, so then the question becomes, well, how do we adaptively represent the problem? There are some heuristics and some algorithms people have developed, again, for the very classic static problem that has been considered in computer science for a few decades now. But none of them are super adaptive. And many of them are very, very high overhead because it turns out this is a very computationally complex problem. All right, so I'll try to skip over some of the more complicated notation in the interest of time. So let me introduce how we decided to model the problem in order to enable this sort of adaptivity. So what we decided to do is we decided to apply reinforcement learning because reinforcement learning is sort of inherently adaptive and it's very expressive. So it allows us to solve these sort of very complex problems by using a neural network to learn a policy for how we do these placements and how we adapt these placements. So if you're familiar with the technical part of reinforcement learning, in order for RL to work, one has to specify three things. The first thing is the state, which tells you sort of what you're dealing with and what is the current state of the environment. In our case, our states are the current placement of our application on our devices. And our action, which is the second thing we have to specify in reinforcement learning, is one task new placement. So in our reinforcement learning problem, what we're allowed to do is we're allowed to look at the current placement of tasks on devices, and then we're allowed to pick one task and move it to one device. So our action is just which task are we going to move and where is it going to go? And then the third thing we have to specify is the reward of reinforcement learning. And we can specify a lot of different sorts of rewards. As you can imagine, different IoT applications may care about different things. But for the sake of simplicity, let's say we're going to specify the reward as the total completion time. So the amount of time it takes for a piece of data to go from the beginning of the application to the end of the application and extract whatever insights we need to extract from this data. So this is a two-task graphical example of what this Markov decision process looks like. As you can see, it looks rather complicated, even though there's only two different tasks in our application. So it's a very simple application. So you can imagine as we get to more and more complex applications, this becomes really, really complicated. So all that is to say, it's not really possible to solve this by hand. And instead, we turn to reinforcement learning. So again, with reinforcement learning, the idea is you specify a state space, which tells you all the different possible states of the environment. And the idea behind RL is that you want to learn a policy that takes a specific action given the current state of the environment. So given the way the tasks are currently placed in the network and all the different resource constraints that are currently operating in the network, now we have to choose a task and we have to choose where to move it. And the idea behind RL is that we'll learn a policy that always tells us, given this state, here is the action that you should take. All right, so this is how we learn the policy, and this is what our policy looks like. Again, I know this looks kind of complicated, so I'll try to sort of just break it down so that you can at least see the different components, although I won't have time to get into the details. So the idea is we first derive a representation of the state, which is sort of inherently adaptive and can accommodate these dynamics in IoT networks that typically occur. The output of this representation, so this representation is a graph. This gets placed into a graph neural network. And then the graph neural network tells us sort of what is the expected reward that we get from each possible action. And from that, we are able to choose an action. So this is the structure of our policy. Now, the main things that we have to do to learn this policy are first, figure out how we're going to represent the state. So what does this graph look like? How do we make this graph? Then we have to learn the weights of the graph neural network. And then the output of the graph neural network gets passed through a multi-layer perceptron. So we have to learn the weights of this multi-layer perceptron. And then we just sample from all of our different possible actions in order to choose an action to take. So this whole structure starts out with a state and then ends with an action. So this is a policy in reinforcement learning. It's telling us, given this input state, here is the action that you should take. All right. So most of our work and most of the challenges in this work actually had to do with how do we actually represent the state so that it is sufficiently adaptive to the environment. So in particular, one of the things we were struggling with is that we may have different numbers of IoT devices available at different times. So again, if you think of like a sensor network, where you have a bunch of sensors collecting data spread over a huge environment, some of them may lose power, some of them may lose connectivity, and your reinforcement learning state has to be able to accommodate that. So how do we do that? The way we do that is by something called the GPNet representation. Where instead of using our device network or our application graph to represent our state, we're going to combine all of that into one gigantic graph. So this is a really, really big graph. And the idea is each node in the graph is a feasible placement of one task on one device. So the size of this graph is also going to change, right, depending on how resource constraints change. And the edges between devices here, between nodes here in our GPNet, just represent which are feasible replacements and which are current placements of tasks on devices. So I know I'm sort of skipping over this, so don't worry if you don't understand the details, but basically we've constructed a gigantic graph, and the size of this graph can sort of change and adapt as needed to adapt as the environment changes. All right, so this gigantic graph then gets fed into a graph neural network, and what this graph neural network does is it says for every single node in my GPNet, I am going to output an embedding. And this embedding now gets fed through the policy network. And at the end of this policy network, what we get is the expected reward corresponding to each node of the graph neural network. And now the cool thing about how we've constructed GPNet is that each node in the GPNet represents one of our actions. Because remember, our actions are choose a task and place it on a device. And each GPNet node is exactly choosing a task and placing it on a device. So what we've done is we've essentially estimated the expected reward that we get from taking each of our actions. And now it's very easy to look at these expected rewards and choose an action and then take that different action. So this is how our solution works. So again, the goal here is now to learn these node embeddings and then choose this optimal action. And of course, there are lots of parameters that we have to learn here. So we use some standard reinforcement learning algorithms to learn the parameters in these neural networks. Okay, so onto the evaluation. So we compared the performance of our solution, which we call GIF, for generalizable placement learning, compared to a random baseline and something called place2, which is also a reinforcement learning-based placement algorithm, but it's very static. It doesn't have the adaptivity that our representation does. And here what I'm doing is I'm computing the normalized completion time. So we want this to be as low as possible. And you can see that compared to place2 and compared to these random baselines, GIF and its variants do much, much better. So it has a much, much lower normalized completion time. And these are on randomly generated graphs. So there's a huge variation in the environment. This is what the other thing we want is GIF really has the device ranges. So what we on the X, I have changed devices. See that which is line has a consistent. On the other hand, two is the static reinforcement learning. It's worse and worse over time. And that again is cannot adapt device network changes. So if device in and out of the network, you cannot change policy, it's going to perform badly. And so policy. My wife table. Let me look at the presentation. All right. So I was saying to evaluate or not whether or not we were able to adapt the solution as the device changes. And the answer is we were. So we did is changed the number in our network, and our solution is GIF, and we also applied the random, and we applied place2 very static learning algorithm. All right. See, is my voice now or? Okay.
A little bit bursty.
I see. Let me switch to a better network. I apologize for this. All right. Can everybody hear me? Okay, great. Okay, I apologize for the interruptions. So we were trying to evaluate whether or not our solution was able to adapt as the device network changed. And in fact, we were able to. So you can see that as the device network changed, we have a very stable performance. We have the straight line at the bottom. But these other non-adaptive solutions got worse and worse as the network changed. And again, that's because they were unable to adapt with the changes to this network. We also evaluated we tried to evaluate what our solution was doing. And here I have a histogram of the number of times each task was relocated. So you can see that most of the tasks are only relocated infrequently, but there were some tasks that were relocated very, very frequently. And our conjecture is that this is because some of the tasks are very, very connected to each other. So where they are placed can have a huge influence on the overall network performance. So those were relocated more often. All right, so that was the end of the first part of the talk. So to summarize, we introduced this framework and representation for adaptive task placement. We formulate placing computational tasks in an IoT network as an iterative process of placing individual tasks. We adapt the representations as the device network changes over time, and we use a reinforcement learning algorithm to learn an optimal placement policy, validating our framework via experiments in different application settings, including on autonomous vehicle graphs. So our future work includes learning policies in an online manner for multiple tasks. So in IoT networks, you usually don't just have one application that you're trying to run. You may have many of them. And we're also exploring other placement objectives. So theoretically in reinforcement learning, you can specify sort of whatever objective or reward you want. But we've only tested our solution on the idea of optimizing completion time. So there could be a lot of other things, for example, reliability, that one might want to optimize that we could explore in our placement framework. All right, so in the second part of the talk, I wanted to switch to focusing a bit more on the communication side of things. So this is work that appeared a couple years ago in a conference called ACM MobiHawk. And the challenge that we're trying to address here is to say, all right, let's assume that we've sort of placed all of our tasks on all our IoT devices. Now what we have to do is we have to allocate communication resources between these devices to make sure that we're able to communicate as needed between these different tasks. So this falls under the umbrella of something called online resource allocation. So we're trying to allocate communication resources in an online fashion. And it's called correlated combinatorial bandits because this is the technique that we're going to use for this online resource allocation. All right, so what is online resource allocation? Well, the basic idea is we are trying to allocate resources to different entities subject to a budget constraint. So of course, this applies in wireless settings, right? Because we have a finite number of wireless channels, so they have to be allocated to, to our different users. But it also applies in lots of settings, like in product manufacturing, stock investment, et cetera. And this would be a simple problem, except that there's a lot of uncertainty in the satisfaction each entity gets from each resource. So for example, in the wireless setting, we may have some estimate of the quality of the wireless channel, but we don't know exactly what the quality of this channel is going to be during the time of communication. And for IoT applications, there's another layer of uncertainty layered on top of this, which is that we may not even have a good idea of how important this communication is. Because the application is not going to tell us like, oh, this data stream is a lot more important than this data stream. It's just going to say, here's all the data I want to communicate. So we may have some uncertainty in how important different communications are, and therefore what priority they should get in the resource allocation. Now, what saves us and what allows us to deal with this uncertainty is that we can try to repeat these allocations over time. So this gives us an opportunity to look at an allocation, observe its results, and learn from our observations. And that's the key to our online learning-based solution. All right, so the motivation behind our work is that we can take off-the-shelf online learning solutions, apply this to our problem, and get probably a decent solution. But what we're trying to do in this paper is to say, For this particular example of resource allocation, we can actually do a lot better than that because we can take advantage of what the resource allocation problem looks like to learn faster. And on this slide, I was trying to sort of give the intuition behind that. I'll go a little bit more into the math in the subsequent slides, but this is really giving the intuition. And the idea is that in resource allocation, I can allocate, different amounts of resources to different users, and I'll get a certain profit or utility from that allocation. And then I have market conditions, which are going to make the profit I get uncertain. So the idea for this problem is that, let's say I allocate a certain number of resources to users, I get a certain profit, let's say P1. Now, if I have some knowledge about how the profit varies depending on the market condition, I might actually be able to figure out what the market condition was at this particular time. And if I can figure out what this market condition might be, so for example, here, I know if I got profit P1 from allocating some amount of resources, then that means I'm either here on this graph or here on this graph. So I know that my market condition, so market condition here could be something like importance of the application. The importance of the application is either here or here. And that gives me, excuse me, information about how good other resource allocations might have been. So the intuition is, if I know how good a particular resource allocation was, I have some information about how good another resource allocation might be. So setting aside these graphs for the moment, if you just think of it as, if I had given more resources to a particular user, they probably would have been even happier than they were if I gave them, the amount of resources I actually gave them. And that allows me that gives me more information about how I should be allocating resources and what the user utility would have been from different allocations. And that's going to allow me to learn faster. All right, so let me skip over some of this related work. As I said, many works have studied online resource allocation using machine learning, but none of these works try to exploit these sorts of correlations between the rewards of different resource allocations. So that's what we're going to do in this work. Okay, so these slides have a few equations, so I'll try to explain what the equations mean and give the intuition behind them. So this is how we formulate our problem. So we want to maximize the expected sum of what we call the utility. So this FK function is the utility, which gives a user satisfaction from getting a certain amount of communication resources. And this depends on the amount of resources we give the user, which is A, and some random fluctuations, which are X. And we're not allowed to observe X, which is what makes this problem hard. And we're also only allowed to allocate a certain amount of resources Q across all these different users K. So we have a constraint on what we're allowed to allocate to users. So this is our problem. And this problem sort of repeats many times, right? As I said, we're allowed to do repeated allocations. So our random fluctuations are going to vary with time t, and our actions are also going to vary with time t. So this is the optimization problem we want to solve on a mathematical level. And what we're going to do is we're going to actually discretize this problem. So we're going to say we're only allowed to allocate certain units of resources. And once we do that, this arbitrary function fk just becomes a set of coefficients mu ik. So I here are the discretized amount of resources. So let's say 1 unit, 2 units, 3 units, etc. And now our goal becomes, can we learn these coefficients for each unit of resources that we give to each particular user? So our goal is to learn these coefficients mu, and then we assume we can just solve this optimization problem. All right, so before I get into our solution algorithm, how are we going to measure the success of our application, of our allocation? Well, we do that with something called the expected total reward. So all this says is, given whatever allocation we've made across these users, this is the expected reward that we're going to get from that allocation. And in online machine learning, a very common metric that we use to measure sort of the goodness of this reward is something called the regret. So what the regret does is it says, suppose I had perfect information about how happy each user is going to be with a particular allocation. Then the optimal allocation is going to be something called S star. I am not allowed to observe S star, but I know it exists. And theoretically, I can try to quantify the gap between this optimal allocation and the actual allocations that I gave users at different times. And our goal is to try to make this regret as small as possible. That is, our goal is to take the actual rewards users got and make them as close to the optimum as possible over time. So this is the main metric that we're going to be using to evaluate how good our solution is. All right, so this is the basic problem setup. Now, as I said, the intuition behind what we're going to do here is we're going to say that our allocations of different amount of resources are going to give correlated rewards. So if I give a certain amount of resource to a user, that means that if I give more resources to this user, they're going to be even happier, they're going to have an even higher reward. And that induces a statistical correlation between the rewards that I observe for different actions that I take. So in particular, we can define what I call here pseudo rewards. So pseudo rewards are just saying, given the reward I experience with a particular action, that so reward given. Let me skip the technical. But constructed reward algorithm. The idea is, and this is similar to the up down algorithm, familiar with bandits. The idea is have all right, can everybody hear me?
Yeah, hi, Carly. Welcome back.
Okay, great. Yes, I'm sorry, I don't know what's going on with the internet today. All right, so again, this is the algorithm that we're going to use. So in the interest of time, let me go through this quickly. So the idea is we have a bunch of potential actions or allocations. And what we're going to do is we're going to estimate the reward and the pseudo reward of each potential allocation using all the data we've gathered from past observations. And then we are going to choose an allocation. So what we're going to do is we're going to assume that the pseudo rewards are the actual reward that we're going to get. And then we're just going to solve our optimization problem, assuming these pseudo rewards are correct. And then we're going to take the whatever action comes out of the optimal allocation problem and update the, do that allocation, observe what happens, and then update our rewards and our pseudo rewards. And this keeps going for many different iterations. The sort of punchline here is that if we look at our regret, which again is the thing we want to minimize, we see the regret has this form here. So it's a constant times something that's logarithmic in the number of iterations plus another constant. So the fact that this is logarithmic in the number of iterations is exactly what we want, because what this is saying is that if we divide this by the number of iterations, then our regret is going to go to 0. Meaning that if we repeat this enough times, we're eventually going to learn the optimal allocation. And what's really interesting here is what this coefficient C represents. So C is the set of what we call competitive base arms. So what is a competitive base arm? Well, the idea is it's just arms that, based on our knowledge from these pseudo rewards, are very unlikely to be part of the optimal allocation. So basically what it's saying is that we can exploit some of our correlations to eliminate some of the possible allocations that we otherwise would have had to consider. So in particular, for some types of reward functions or utility functions, we can actually get C equal to 0, meaning that we can eliminate all possible allocations except for the optimal one very, very quickly. So if we look at our regret metric, what we'll get is that the regret goes to 0, not just logarithmically in t, but actually the regret is just a constant. And this constant holds for any t. So this is a much, much faster decrease in the regret compared to what we would have gotten if we had not exploited any sort of correlations. So basically what this is saying is that we can learn much, much faster by exploiting these correlations in our resource allocation. All right. So my last few slides are just us evaluating this algorithm for some practical settings. So the first setting that we looked at was allocating users to different wireless access points. So here we were using a wireless trace from Sweden that measured the number of active users at each access point. And the idea is you have a bunch of incoming users and you want to assign them to each access point so as to maximize throughput. So here UCB-RA is an algorithm that does not exploit correlations. Core UCB-RA is our algorithm. And you can see that we learn much, much faster. We have much lower regret compared to UCB-RA without correlations. Another example is power allocation to wireless channels. So the idea is we have 1 unit of power that must be assigned to 4 communication channels. We don't know exactly the noise of each channel. So the optimal solution here would be a water filling solution. And the objective is to maximize the throughput of each channel. The challenge here is that we can only observe the reward if more than a certain amount of power is allocated to this channel, otherwise it gets lost in the noise. So this is the regret that we observe in this case. So you can see UCB-RA without correlations has a very high regret. We have a much lower regret, which is this blue line here. And if we actually allow observing this reward for any amount of power allocated to each channel, we actually get a 0 regret. And that's because if we're allowed to observe the throughput of the channel, no matter what this AK is, we can actually reverse engineer what this XK is. So that means that we can essentially eliminate all of the uncertainty in our allocation problem because we can know exactly how much noise there was on each particular channel. And that is going to allow us to learn very, very fast. So we essentially learn the optimal solution almost instantaneously with very few iterations. All right, so these are my last couple slides. So to summarize this part of the talk, we introduce a correlated combinatorial bandit framework for online resource allocation, where we're exploiting correlations between different allocations in order to very rapidly learn what is the optimal allocation. And we're able to even theoretically prove that we get a better performance by exploiting these correlations. We also validated this on experiments in different wireless application settings. So in our future work, we are looking at how do we learn correlations in a more online manner, and how do we do continuous budget allocation with correlations. So our current work only works if you have discrete budget allocations, but of course in practice you may have more continuous allocations. So to recap the entire talk, so again, going back to the motivation here was how do we enable distributed applications to run over IoT networks by provisioning both the computing and communication resources they need. So some of the future directions we're looking at are first application-specific task distribution and resource allocation. So we have collaborations with some researchers in augmented reality and vehicular crowd sensing to enable these environmental awareness applications for AR and for large-scale vehicular environmental monitoring. Federated learning was one of the applications I introduced at the beginning. And we're also looking at different variations of federated learning. One of the big challenges that we had to address here was the dynamics of the environment and adapting and being resilient to different dynamics. So we've been considering resilience not just in terms of adapting to dynamics, but also to adversaries who may want to sort of fool us into making the wrong decision. So some of the things you can do here are things like building in redundancies to resource provisioning, trying to, again, enable resilience to adversaries in these more collaborative sort of applications. And some of these models can also be very application specific. For example, in augmented reality, there's been some work recently in overcoming adversaries in augmented reality. And the final direction that we've been looking at is aligning decisions with human intent. So the idea here is that the user at the end of all these IoT applications is very often a human being who needs to interpret the data and use whatever the application is producing. So we would like to make sure that we provision the computing and communication resources and design the application so that it's most useful to the user. And this adds another layer of uncertainty because we never quite know what the user exactly wants. All right, so with that, I'll stop here. Thank you very much for listening, and I'm happy to take questions in the few minutes we have remaining.
Thank you very much, Carly. I think it's truly interesting talk. I'm full of questions, but
right.
there are two here. Let me take those two. So the first question Yasin is asking, how can online machine learning algorithms be optimized? I'm not sure whether that's the scope of your work, but let me ask anyways. So there is that question, online machine learning algorithms optimization, especially in the context of dynamic and heterogeneous nature of data in the distributed application. Then also there is a second part about what are the best practices for model adaptation and validation in such environments. Yeah.
Okay, yeah. So to the first part about how online machine learning algorithms can be optimized for these sorts of adaptive and dynamic settings, I think a lot of the work there focuses on how do we learn faster, right? So how do we extract the maximum insights we can get from our data so that we don't have to waste time sort of training our models. We can just deploy them and get the optimal solutions. So some of the work that I was doing in the second part of the talk was sort of about that, right? Really trying to exploit all the correlations that are inherent in the problem structure to accelerate these online machine learning algorithms. And I do think there's some potential to do that, especially in communication settings where we know a lot about the structure of these problems. There should be ways to take our knowledge of the structure of those problems, embed that into the online machine learning, and allow us to learn much, much faster than we would have with off-the-shelf algorithms. And then I think the second part of the question was about sort of model validation. So I think that has been sort of an ongoing challenge, especially in the communications setting, right? There's not that many data sets available. Many of the data sets could be hard to work with. So in the work we did in this talk, we were lucky enough to first have collaborators who were able to generate data sets for us. Of course, those aren't sort of large scale data sets, but at least they allow us to do some initial validation. So that's one potential way to validate a model or an algorithm. I think there are several initiatives to collect these sort of large scale data sets in more computing or communication driven applications. So getting away from the default like image recognition applications. So I do have some hope that those can be used for model validation for these online learning sorts of algorithms. And I think the community has sort of recognized that this is a big challenge and is trying to solve that.
Thank you very much. And the second question, by the way, before I go there, I think ITU has data sets and we host challenges.
Yes,
especially
yeah.
in such it's as you say, going beyond images and so on. There are wireless and network related data sets that we host. Let me go to the next question. Blessed, very quickly, can you comment on the scalability of your framework that you described? Especially the graph will grow over a period of time, maybe based on the number of devices and tasks. How do you comment upon that?
Yeah, so scalability is a big issue in this problem. And yes, the graph that we construct will grow very rapidly as we have sort of a large number of tasks. So I do think that could be a limitation as we look at really massive sort of IoT applications. So we are trying to look at some solutions for that. So some solutions could be a sort of hierarchical placement where you group tasks together to have a sort of smaller application graph. And then once you place that, you look at the tasks that comprise that sort of node that you created. So there are certainly ways to get around it. But I think this problem is just inherently very, very large scale. As I said, the static version, I think, is computationally NP hard. So unfortunately, there's no good way to get around this sort of scalability issue.
Okay, thank you. Miller is actually asking one of the questions which I had. I mean, there are two conflicting things, or rather, the regret versus reward. Is there any quick comment?
Yeah, so mathematically, they don't actually conflict. So if you maximize your reward, you're actually going to end up minimizing your regret because you'll be getting as close as possible to the optimum. The reason that we look at regret is just because theoretically it's easier to work with if you assume you have some sort of benchmark. And it sort of normalizes our metric across different problems so that we can sort of compare them in a fair manner.
Great. All right. So yeah, thank you very much, Carly. And I think we have 1 minute to stop. Back to you, Jang.
Thank you already, everyone, for all your work. And I would like to thank everyone for sparing your time for this webinar, and also for our speaker, Carly, for her contribution. So we have more sessions in the future. So please check the AI for Good program page for details. We look forward to your participation in the future. Thank you for joining and have a very nice day.
Thank you for participating in today's AI for Good session. We hope you've learned something new, innovative, and engaging in today's event. We now encourage you to continue the conversation on the live video wall in the neural network. Here you can ask questions, like and comment, share links, complete the poll, connect with interesting profiles, or speak one-on-one using the chat and video function. We invite you to explore the lobby, try the smart matching quiz, visit the virtual exhibits, poster boards, the eShop, and build your personalized AI for Good program. Let's shape the future of AI for Good.
The AI for Good Global Summit, convened by ITU, recognizes the joint responsibility of governments, the private sector, United Nations agencies, academia, and others to ensure AI reaches its full potential while preventing and mitigating harms.
And it's a moment that calls for action. And today I'm calling on each of you to use this summit to help the world to better understand what kinds of regulations, what kinds of guardrails we need to put in place right now. So together, let's make it innovative, let's make it safe, and let's make it responsible for all. Thank you very much.